Good morning, one and all. Myself, Sreevani, working as an assistant professor in the Department of Electronics and Communication Engineering in Institute of Aeronautical Engineering, Dundigal, Hyderabad. So, in the today's lecture, we are going to learn some of the questions, means in a short answer and long answer, and how the analytical questions need to be answered in the exam point of view. Right? So now we in this particular lecture we will going to discuss about this module 2 question bank under the magnetostatics or static magnetic fields in electromagnetic waves and transmission lines. So state Bayard-Savart's law. So in short way, how we'll define this Bayard-Savart's law means Bayard and Savart are two scientist names who proposed the differential component of magnetic field intensity. So Bayard-Savart's law states that differential component of magnetic field intensity, that is dH, is directly proportional to the current element IDL and the sinusoidal angle between the current element IDL and the point P where we are going to evaluate magnetic field intensity H. And it is inversely proportional to the square of the distance between two. Those two are current element as IDL and the point P at which the magnetic field intensity is to be evaluated. And this proportionality constant is replaced by K, and that K is given by 1 by 4 pi. Hence, dH bar is equal to IDL into sine alpha by 4 pi r square is the statement for the Bayard-Savart's law. Okay? Differential component of magnetic field intensity is directly proportional to the current element IDL and the sinusoidal angle between the current element IDL and the point P, and it is inversely proportional to the square of the distance between current element IDL and the point P at which the magnetic field intensity H need to be evaluated. So dH is equal to IDL into sine alpha by 4 pi r square. Generally, this H is magnetic field intensity H is expressed in terms of vectors. Means in order to express this in terms of vectors, we just replace sine alpha by vector form. Means it can be given by IDL into AR by 4 pi r square. Right? Where AR be the unit vector normal to the r direction. Next, state Ampere's force law. So this Ampere's force law is given by the force between two current elements, and it is represented with respect to the flux density. Then that is given by B12 or B1 is given by equal to closed line integrals L1 and L2 mu naught I1 I2 by 4 pi into dL1 into dL2 into AR21 by R21 whole square. Right? This is what the Ampere's force law. It is obtained between the two current elements. Hence, the first current element is related to the loop 1. We will consider it as I1 dL1. And if you consider it for the next second to loop is I2 dL2, then the flux density B can be expressed as here closed line integrals L1 and L2 mu naught I1 I2 by 4 pi into dL1 into dL2 into AR21 by R21 square. Suppose if you want to write it for the B12, then the directions need to be in the reverse order. Next is state Ampere's circuit law. So in order to write the statement regarding this Ampere's circuit law, it is also called as Ampere's law, means line integral of L in any closed path, and it is represented in the vector form of magnetic field intensity H dot dl is equal to net current enclosed by that path, and it is given by integral S J dot ds. So I enclosed is equal to closed line integral LH dot dl, or sometimes it might be expressed in terms of current densities, means integral S J dot ds. Yeah, this is the Ampere circuit law. In short, we'll call it as Ampere's law, and it is the one of the Maxwell's equation to be derived for the magnetostatic fields. Next is magnetostatic field is conservative. Explain. So similar to that of electric field is conservative case, but here the magnetic field is not conservative. So previously we have considered for del cross E bar equal to 0 case, electric fields are always conservative by the nature. Whereas here if we consider del cross H equal to J, which is not equal to 0. This is the case we can say that magnetostatic field is not conservative, right? So curl of a magnetic field intensity is given as according to the current density, so which is not equal to 0 case, magnetostatic field is said to be not conservative. Okay. Then write the Maxwell's equation for the magnetostatic field. Right? One of the Maxwell's equation which is to be derived in magnetostatic fields is from Ampere's circuit law, that is given by closed line integral L H dot dl is equal to I enclosed or integral S J dot ds. So integral form of the Maxwell's equation means integral L H dot dl is equal to integral S J dot ds, or by applying proper Stokes theorem to this equation, then point form or integral differential form of this equation need to be written as del cross H is equal to J, where H be the magnetic field intensity and J be the current density. Conduction current density. Next, define magnetic vector potential and magnetic scalar potential. So to define this magnetic vector potential, we just consider the notation as A bar, and the scalar potential we used to consider it as Vm. As we have considered electric scalar potential as V, and Vm stands for M is for magnetostatic fields and V is the notation for the scalar potential. And the magnetic vector potential A bar can be represented with the help of the notation we are considering as with respect to A bar, right? And the relation between two are given by del cross means magnetic flux density B bar is expressed in terms of magnetic vector potential means B bar is equal to del cross A bar, where A bar be the magnetic vector potential and B bar be the magnetic flux density. Right? Next, write the expression for Lorentz force equation. So this Lorentz force equation, to get the equation for this Lorentz force equation, we need to consider the fields associated with the electric as well as magnetic fields force equations we just considered. So Fe means total F, or Lorentz force equation is given by here F is equal to Fe plus Fm, where Fe stands for electric force and Fm is for magnetic force. And in general, we can express this in terms of as Q into E plus U bar cross V bar, right? So Fe can be given as electric force, Fe can be given as Q into E bar, whereas magnetic force is given as Fm bar equal to Q into U bar cross V bar. Then total equation, or the Lorentz force equation, by combining electric force as well as the magnetic force, then it becomes F equal to Fe plus Fm. Then from that, Q into E plus U bar cross V bar, where Q be the charge and E bar be the applied electric field, and U bar is then velocity of an electron, and V bar be the magnetic flux density. So the force due to electric as well as magnetic fields equation is to be considered as a Lorentz force equation, and it is given by Q into E bar plus U bar cross into V bar. Next, some more short answer questions in the magnetostatics, or define inductance and what is the energy stored in an inductor. So inductor is a conductor which is able to store magnetic energy in the form of currents. So the property which exhibits by the inductor is said to be inductance, and generally it is measured in henries. And what is the energy stored in an inductor? So, and inductor generally we used to consider it as the L, and the energy stored in an inductor can be represented as half into L I square. The energy which is to be stored in the inductor is given by Wm is half Li square. And what is the value of permeability for free space, and specify its units. What is the value of permeability for free space medium? So permeability of free space is represented with mu, and free space medium representation is considered to be as mu naught. And mu naught is equal to, the value is given by 4 pi into 10 power minus 7, and the units are represented as Henry per meter. As similar to that of free space permittivity in electrostatic fields, as epsilon naught is equal to 8.854 into 10 power minus 12 farad per meter. Why? Because there all the voltages are electric voltages are represented with capacitances, and generally that capacitance is measured in farads. Now here we are talking about the currents, means all the currents are represented in the fields case. We are considering it with magnetic fields. Right? Hence, free space permeability is represented with mu naught, and its value is given by 4 pi into 10 per minus 7 Henry per meter, and units are given by Henry per meter. And write the Maxwell's equation for steady magnetic field both in point and integral form. Right? So Maxwell's equations for steady. So in the static magnetic fields, we'll have two different Maxwell's equations. One is from the Ampere circuit law, that is integral form is given by closed line integral around any path which is represented with magnetic field intensity, that is closed line integral L H dot dl is equal to I enclosed, nothing but integral S J dot ds is the integral form, and the point form can be by applying Stokes theorem. Then it becomes del cross H bar is equal to J is said to be point form or differential form of the Maxwell's equation, which is to be derived in the first Maxwell's equation to be derived in magnetostatic fields. Coming to the second one, then integral form is closed surface integral S B dot ds is equal to 0, and then by applying proper divergence theorem to this, then it becomes del dot B equal to 0. Means we cannot separate the magnetic bar into two parts, or isolation of magnetic charge does not exist case, we will consider the second Maxwell's equation to be derived in the case of steady magnetic fields. Right? So the first one is to be obtained from Ampere circuit law, and the next one is to be obtained as the magnetic monopole does not exist in any closed connecting paths. Then list the boundary conditions for magnetic fields. So between two magnetic media, we have got two different boundary conditions related to the normal as well as tangential components. So tangential components case, it can be written as H1t minus H2t equal to K. If K equal to 0, if current density K is equal to 0 case, then H1t equal to H2t. And the second Maxwell's equation, second boundary condition is given by here B1n is equal to B2n. Right? Related to the tangential components means we can say that H1t is equal to H2t if K equal to 0. So where K be the surface current density, if that surface is free of current density, means if K equal to 0, H1t equal to H2t, this is the case, we can say that the tangential components of both the magnetic field intensities in medium 1 and medium 2 are continuous across the boundary. Similarly, B1n is equal to B2n can be considered as normal components of both the magnetic flux densities of medium 1 and medium 2 are continuous across the boundary. Similarly, if we consider in place of tangential components magnetic flux densities, then tangential components of magnetic flux densities are discontinuous across the boundary, and normal components of magnetic field intensities are discontinuous across the boundary. So generally we used to consider the two boundary conditions for magnetostatic fields is H1t is equal to H2t and B1n equal to B2n. Then state Gauss law for magnetostatic fields. So the Gauss law for the magnetostatic fields is given by closed surface integral s b dot ds is equal to 0 is the integral form, and by applying divergence theorem to this, then it becomes del dot b bar equal to 0. Divergence of magnetic flux density is equal to the 0. A closed surface integral s b dot ds is equal to 0. This is the case. We can see that the statement regarding this is magnetic monopole does not exist in any closed conducting surfaces. Then define displacement current density. As we have discussed the two types of current densities in the case of electrostatic fields as conduction current density and convection current density, then in the time varying fields or magnetostatic fields, we use one more definition, one more current densities exist, that is displacement current density, where electric displacement or electric flux density is represented with d bar, and the change in this one means rate of change of magnetic electric flux density d bar with time is given by displacement current density, and it is here dou d bar by dou t is equal to jd, right? So for all the time varying fields, if you replace dou by dou t by j omega, then jd becomes j omega into d bar or j omega into epsilon into e bar, right? So displacement current density that is represented with jd, and mathematically we can write the equation as jd is equal to dou d bar by dou t, and for all the time varying fields, the variation with respect to the partial derivative and the change if you consider with respect to the time t, and that will be replaced by here j omega, hence jd is equal to j omega d bar, and the relation between d and e if you substitute as epsilon into e, then it becomes j omega epsilon into e bar. Next, define Faraday's law. So now to define this Faraday's law, the induced EMF in any closed conducting path, that is VEMF, is directly proportional to the time rate of change of magnetic flux linkage factor, and it is given by d lambda by dt. Right? If you consider d lambda, lambda is equal to n psi, then VEMF is equal to n into d psi by dt. Right? Induced EMF in any closed circuit is directly proportional to the time rate of change of magnetic flux linkage factor, that is d lambda by dt. And if you replace here magnetic flux linkage factor as lambda with n psi, where n be the number of turns in the coil and psi be the flux through each turn. Hence VMF is equal to n into d psi by dt. If we consider n value as for a single turn, VMF is equal to d psi by dt. Okay, next, what is meant by transformer EMF? So depending upon this Faraday's law, one of the Maxwell's equation for the time varying fields, we will define two types of EMFs. One is transformer EMF and another one is motional EMF. So for all the stationary charges, the produced EMF is called as transformer EMF, and it should be given by here VMF is equal to minus d psi by dt. And if you consider in place of psi by, if you substitute flux density, hence it is VMF is equal to minus d by dt integral v dot ds. Okay, this is the transformer EMF. It is produced due to stationary action, hence it is the name has given as transformer EMF. Give the expression for energy density for magnetostatic fields, and this is given by, generally for energy representation we use the notation as W, and for M stands for magnetostatic fields, and it is given by half integral V B dot H dV or half integral V mu into H square into dV, where B is the magnetic flux density and H be the magnetic field intensity and mu be the permeability of the magnetic fields, right? Permeability of the material. And relation between B and H means if you substitute B equal to mu into H, then half into integral V mu H square dV can be considered. So this is the energy density in magnetostatic fields equation, that is Wm equal to half integral V VH dV or half integral V mu H square dV. And similarly, energy density in electrostatic fields means B is analogous to D in electrostatic fields and H is analogous to E in electrostatic fields. So next one. Define magnetic flux density, then specify its units. So magnetic flux, as we know that flux means number of lines of force and density means which is passing through a given area, and related to magnetic fields means magnetic lines of force which is passing through a given area is represented with the magnetic flux density, and it is given by the notation as V bar equal to mu into H bar. Hb the magnetic field intensity and mu is the permeability of the material, and we can write the equation as here. The units are Weber per meter square, or sometimes it is to be measured in terms of Tesla. Generally, magnetic flux is measured in, or magnetic charge is measured in Webers, and it occupying some area means density, then we should measure it in terms of Weber per meter square or Tesla. Next, what is the value of permeability for free space and specify its units? As we know that the permeability is represented with mu and the notation is given by mu naught, then its value to be 4 pi into 10 power minus 7 Henry per meter. Permeability of free space medium is represented with mu naught and its value is 4 pi into 10 power minus 7, and we are measuring it in terms of Henry per meter. Now, what is the inconsistency of Ampere's circuit law? So, according to the Maxwell's equation, then del cross H bar is equal to J bar. Right? According to the conservative nature of electrostatic fields, del cross E bar equal to 0, but here del cross H bar is equal to J, which is not equal to 0. But according to J, this is means if you apply divergence of on both sides of this one, del dot del cross H bar is equal to del dot J, which is not equal to 0. Okay, so see, if this one is equal to 0, then this is the case if it is del dot J bar equal to 0. But according to this formula, del cross H bar is equal to J, then which is not equal to 0. So if we compare to, there is a confliction in the formula, then we are going to add one extra term to this J called displacement current density, and it is given as del cross H bar is equal to J plus JD. For a free space means if you consider J equal to 0, then JD is exist, then that is given by displacement current density, and it is given as JD equal to dou D bar by dou T, and JB the conduction current density, and it is given by sigma into A bar. Right? So this is the way the inconsistency of Ampere's circuit law is eliminated by adding displacement current density to that particular law. Next, coming to the long answer questions which are exist in the magnetostatics under in electromagnetic waves and transmission lines. So state Biot-Savart's law and obtain the expression for magnetic field intensity at a point P due to line current element. As we know that Biot-Savart's law means it derived the equation for differential component of magnetic field intensity, that is dH bar is directly proportional to the product of ideal and the sinusoidal angle between ideal and the point P, and it is inversely proportional to the square of the distance between two. So if we evaluate, or if you want to express this in terms of point form, that should be ideal into AR by 4 pi or whole square. So proportionality constant is replaced by K and its value is given as 1 by 4 pi. Hence dH bar is equal to ideal into AR by 4 pi R square. So depending upon the assumptions, if you want to find the displacement of DL in the R direction, and finally you're going to get the magnetic field intensity DH component in terms of the line current element. Okay. Next, describe the inconsistency in Ampere's circuit law, how it is rectified by Maxwell. right? So just now we have seen that is del cross h bar is equal to J. That is point form or differential form of the Maxwell's equation, that is del cross h bar is equal to J, can be obtained. Now, by applying divergence theorem to this, means both sides, if you consider divergence of this one, del dot del cross h bar means divergence of curl of any vector field, that is del dot j is equal to 0. But here, according to continuity of current equation, that is del dot j is equal to minus dou rho v by dou t. Right? So here del cross h is equal to del dot j is equal to 0 here. According to this, del dot j is equal to minus dou rho v by dou t. So there is a confliction in the formula. Then to avoid this one, we will add one extra term to this RHS part of Ampere's circuit law, which is to be derived in Ampere's law, that is del cross h bar is equal to j plus jd. And by applying this one, del cross means del dot del cross h is equal to del dot j plus del dot jd. So by equating this to 0, then which is equal to del dot j plus del dot jd. Now from this, del dot j can be written as minus del dot jd. So this is the case that del dot j is not equal to 0. This is the way he was rectified the inconsistency which is exist in the Ampere's circuit law. Let's describe in detail about Faraday's law of induction and write the mathematical statement of this law. So according to the Faraday's experiment, he concluded that the induced EMF in any closed circuit that is represented with EMF is directly proportional to the time rate of decrease of change with respect to the magnetic flux linkage factor, and it is given by minus d lambda by dt, which is equal to minus d lambda by dt into n psi. Then minus n into d psi by dt. For a single turn case means if you consider n is equal to 1, then VEMF is equal to d by dt integral b dot ds. Or VEMF is equal to minus integral s dou b bar by dou t. Right? So this is the integration form, or induced EMF in any closed circuit is given in terms of field intensity as E dot dl. Right? This is the integral form. Then if you consider the point form for this, then it can be given by del cross E bar is equal to minus dou v bar by dou t. This is the point form or differential form of the Faraday's law, which is to be derived in time varying fields or electromagnetic fields. Derive Maxwell's equations in integral form and differential form of time varying fields. So two Maxwell's equations which are already derived in static, electric as well as magnetic fields need to be modified in time varying fields. One is there is del cross E bar can be modified according to the Faraday's experiments as del cross E bar equal to minus dou b bar by dou t. And according to the Ampere circuit law, in order to avoid inconsistency which is exist in the Ampere circuit law, we will add an extra term to that J as JD, called displacement current density, that is given by del cross H bar is equal to J plus JD. These are the two point form or differential form of the Maxwell's equations which are to be derived in the case of time varying fields. And integral forms means closed line integral L E dot dl is equal to minus integral S dou b bar by dou t into ds is the integral form of the Faraday's law. And here for the according to Ampere's circuit law, that is closed line integral L h dot dl is equal to integral S j plus jd into ds, where J is said to be conduction current density and JD be the displacement current density. Next, define and explain the terms scalar and vector magnetic potentials and how to determine these quantities for magnetic fields. Right? So, as a scalar potential is represented with Vm and vector magnetic potential is represented with A, and the relation between magnetic flux density B and the magnetic vector potential as given by B equal to del cross A bar. Or from this, if you want to write the line current element, surface current element and volume current elements, then the B or mu can be written as B or H can be written as H bar is equal to integral L IDL into sine alpha by 4 pi r square, or integral L IDL into AR by 4 pi r square. Okay. Or if you want to express, this is for line current element, or surface current element means we just replace IDL by KDS, and volume current element means that is replaced by JDV. The three current distributions in the magnetic fields are given by IDL is equal to KDS is equal to JDV. This is for line current element, and here it will be the for surface current element, and this is for volume current elements. These are the different quantities to be measured in the magnetostatic fields. Then derive the expression for Lorentz force equation, and this is to be obtained in the case of by adding electric force as well as the magnetic force. In general, the electric field intensity E can be represented by here E equal to F by Q, force per unit charge when it is placed in electrostatic fields. Now from this, electric force can be given by E into Q. Similarly, if the same stationary charge is moving with a constant velocity, then the field is to be considered as a magnetostatic field, and that is the case. Magnetic force is given by Q into U bar cross B bar. Velocity of an electron is represented with U bar, and B bar be the magnetic flux density. By combining these two, F is equal to Fe plus Fm, then E bar into Q equal to Q into E bar plus U bar cross B bar. Okay, this is the equation is said to be Lorentz force equation. Then obtain the equation for force on a differential current element. So this can be obtained as here F is equal to Fm equal to IDL into magnetic flux density as B. Suppose if you replace it with current element by surface current element, and means that can be written as KDS into B, or sometimes it is written as JDV into B. IDL, KDS and JDV be the three current distribution elements in the case of magnetostatic fields, and B be the magnetic flux density. And obtain Maxwell's equations in phasor form. So phasor form means we just write here, see del cross H bar is equal to, that is J plus JD, and which is equal to sigma into E, means J is said to be conduction current density, and the formula is given by sigma into E, and JD be the displacement current density, and it is given by dou D bar by dou T. So for a time varying fields, that dou by dou T is replaced by J omega, hence it is written as sigma into E plus J omega epsilon into E bar. Now here if you take E as common, then sigma plus J omega epsilon is given by the equation for del bar cross H bar. Similarly, for a time varying Faraday's law case, del cross E bar is equal to minus dou B bar by dou T, and here also if you substitute B by mu into H, then it becomes minus mu into dou H bar by dou T, which is equal to minus J omega mu into H bar. For a time varying fields, that is dou by dou T is replaced by J omega, and this can be written as del cross E bar. Right? Del cross E bar equal to minus J omega mu into H bar, and del cross H bar is equal to E bar into sigma plus J omega epsilon are the two phasor equations for the Maxwell's equations. Next, derive the magnetic boundary conditions between two different media. As in order to derive, we need to use two Maxwell's equations, and to get the boundary conditions between two magnetic media, we use two Maxwell's equations for the static magnetic fields. That is del cross H bar is equal to J, or integral form means closed line integral L H dot dl is equal to I enclosed is the one of the Maxwell's equation, and one more is closed surface integral S B bar dot ds bar is equal to 0. From this, from the first Maxwell's equation, we will be getting the value as H1t is equal to H2t, and from this B1n is equal to B2n. Right? So after dividing two orthogonal components, like H is decomposed into H1t, HT and Hn. Similarly, the same decomposition can be done for B also, where B is also decomposed into two orthogonal components as normal and tangential. Then all the considerations are to be considered. Now according to that, the boundary conditions between two magnetic media means H1t equal to H2t and B1n equal to B2n. So from these two, we can say that tangential components of both the magnetic field intensities are continuous across the boundary, and normal components of both the magnetic flux densities are continuous across the boundary. Then state and explain Ampere's circuit law. So Ampere's circuit law states that closed line integral L around the magnetic field intensity, that is H dot dl, is same as that of the net current enclosed by that surface. That is integral L H dot dl is equal to I enclosed, which is nothing but integral S J dot ds. So by applying proper Stokes theorem to this equation, then it becomes del cross H bar is equal to J. Right? So here the Ampere circuit law gives us relation between line to surface integrals. Next, explain the inconsistency of Ampere's circuit law. So by adding extra term to the conduction current density in the Ampere circuit law, that is del cross H bar is equal to J case, by adding extra term to the JD as the displacement current density, then J plus JD is said to be modified form. Then by applying divergence on both sides of this, del dot del cross H bar is equal to del dot J plus del dot JD. So in the vector analysis, del dot divergence of curl of any vector field is equal to 0 case, then this becomes del dot JD is equal to minus del dot J. So this is the case, the del dot J is not equal to 0. This is the way the confliction which is exist in the, or the inconsistency which is exist in the Ampere circuit law is to be avoided. Obtain the expression for energy density in magnetostatic fields. So to derive the energy density in magnetostatic fields, we need to consider the energy concentrations in the magnetostatic fields. So from that, we'll be getting the value as Wm is equal to 1 by 2 integral V dot H into dV, or 1 by 2 integral V mu into H square dV. Right? So as we know that the relation between flux density and field intensity as V bar equal to mu into H bar, then the same thing is to be substituted over here. Then Wm equal to 1 by 2 integral V dot H dV, which is equal to 1 by 2 integral V mu H square dV. Then explain 4 Maxwell's equations in static, electric and magnetic fields. Right? So in the electrostatic fields, we have 2 Maxwell's equations. One is from Gauss law, that is rho V equal to del dot D, and second Maxwell's equation in electrostatic fields as del cross E bar equal to 0. And 3 and 4 are to be derived in static magnetic fields as del cross H bar is equal to J, and fourth Maxwell's equation for the static, electric as well as magnetic fields as it is del dot B equal to 0. So first two are derived from the electrostatic fields and the next two are derived from the magnetostatic fields. Right? So volume charge density is same as that of the divergence of electric flux density, and here del cross E bar equal to curl of electric field intensity equal to 0, means according to the conservative nature of electrostatic fields, here del cross E bar is equal to 0, and from the del cross H bar is equal to J, curl of the magnetic field intensity same as that of the current density as J, and here divergence of magnetic flux density is equal to 0. These are the four Maxwell's equations which has to be derived in the case of static electric as well as magnetic fields. Next, define Ampere's force law and derive the expression for it. So to derive the Ampere's force law, we need to consider two current carrying loops. One is I1 dl1 and I2 dl2. So the current which is produced in the circuit one is I1 and here it is to be I2. And the distance is to be considered as sometimes R12 or it might be sometimes R21 also. So based upon this, B12 or B21 can be written, that is magnetic flux density in the circuit 2 due to the current element I1 dl1. Or B21 means the flux density which is produced in the circuit 1 due to the current element I2 dl2. And this can be given by here mu naught I1 I2 by 4 pi closed line integral L1 closed line integral L2 dl1 into dl2 into AR by R whole square. Right? This is the equation called Ampere's force law and it is to be obtained between two current carrying loops. Then state Faraday's law and derive the expression for Maxwell's equation for time varying fields. Now, according to the Faraday's experiments, induced EMF in any closed circuit is directly proportional to the time rate of decrease of change in the magnetic flux linkage factor, and mathematically we can write the equation for this as del cross E bar equal to minus dou B bar by dou T is the point form or differential form. And if we want to express that in terms of integral, closed line integral L E dot dl is equal to minus integral S dou B bar by dou T into ds. Okay, this is the one of the Maxwell's equation to be derived in the case of time varying fields as called as Faraday's law. Next, analytical questions which are to be covered in the case of magnetostatic fields. The first problem is a circular loop located on x square plus y square equal to 9, then z is equal to 0 carries a direct current of 10 amperes along and determine h at 0, 0, 4 and 0, 0, minus 4. So here the variables are considered to be as x, y, z means Cartesian coordinate system variables are given, as we know that the differential components are dx, dy and dz. The loop is located at x square plus y square equal to 9 and z is equal to 0 plane we have considered and the direction is to be considered along the z. And the current value is given as 10 amperes, then h is to be evaluated. So h is equal to h is given by I by 2 pi rho into a rho. I by 2 pi rho into a rho, or this is the or h phi direction means I by 2 pi rho into a rho. Using this formula, we can find h is to be at 0, 0, 4 on time and 0, 0, minus 4 at the other time. Substitute in place of whatever the current value and the rho values to be given. From that, we will be evaluating the magnetic field intensity at those two particular points, or 0, 0, 4 and 0, 0, minus 4. Next, given the magnetic field vector potential, that is A is given as A bar equal to rho square by 4 into Az Weber per meter, and calculate the total magnetic flux crossing the surface. So psi we need to find, and phi equal to pi by 2, and rho is ranging from 1 to 2 and z is ranging from 0 to 5. Rho, phi, z are given means we have to consider here the coordinate system is cylindrical coordinate system. Variables are rho, phi, z and differential components are d rho, rho d phi and dz. We need to remember these three differential components which are exist in the cylindrical coordinate system. Depending upon that, first, in order to find this, the total magnetic flux crossing the surface means psi is equal to integral S B dot ds. Then the relation between B and A, that is given by B bar equal to del cross A bar. From this, first get the value of B and substitute this B in here, and we need to write the formula for ds also. Why? Because phi equal to pi by 2 plane, pi by 2 is given, means in the phi direction we are supposed to write the equation as for ds. So phi direction means d rho, the formula for ds is d rho dz into a phi to be obtained. To find this B equal to del cross A bar, we need to write according to the determinant form A rho A phi and AZ, then dou by dou phi and dou by dou Z, and here along with this del cross A bar equal to 1 by rho into, then A rho here, rho A phi here, and AZ here. Now, according to this, we will evaluate the equation for B. Then it should be expressed in terms of a vector form, and along with the phi component only we need to evaluate. And here integral S means we are integrating this one with respect to rho as well as Z, where rho is ranging from 1 to 2 meters and Z is ranging from 0 to 5. And we need to substitute B value, whatever the value which is to be obtained over here, and ds by d rho dz into a phi. Upon that, we are going to simplify the equation for magnetic flux which is crossing that particular surface, and it should be expressed in terms of Webers. Magnetic flux is generally measured in Webers. Next, in a certain conducting region, H is given as yz into x square plus y square into ax minus y square xz into ay plus 4x square y square into az ampere per meter. Then from the given, we need to determine j at 5, 2, minus 3. So if you observe here, all the terms are representing x, y, z. Means the first type of means Cartesian coordinate system or rectangular coordinate system variables are given. Hence x, y, z values are x is equal to 5, y is 2 and z is minus 3. Now the relation between j and h means in order to find a means j here, del cross h is equal to j will be evaluating. So the same determinant form. So ax, ay and az, dou by dou x, then dou by dou y and dou by dou z. Then here hx and hy and hz values need to be considered as j. Why? Because hx is given as yz into x square plus y square, this is hx, and minus y square into xz value as hy, and 4x square y square as hz. So substitute in place of hx, hy, hz by these three and integrate, then expand this determinant form, then you're going to get j in terms of the vector form, right? And after getting the values, you substitute x, y, z values by 5, 2, minus 3 to get the value of j. And j can be measured in ampere per meter square. Okay, then find the current passing through the x. So current we need to find, that is I in terms of j means I equal to integral S j dot ds. See here the variables are y and z are given. Now from this differential components in a Cartesian means dx, dy, dz. Then based upon this, if x is equal to minus 1 means in x direction we are supposed to write, then the formula for ds becomes dy dz into ax. So here we need to substitute in place of j by x component only. And if we are integrating with respect to s means the variables are y and z, then y equal to 0 to 2, z is equal to 0 to 2, then j in terms of ax into ds by dy dz into ax. This is the way if we evaluate, then and finally the current which is passing through that given area is to be measured in terms of amperes. Next, a current distribution gives rise to the vector magnetic potential A is given, and calculate the following at B and the flux through. So the B and A relation, as we know that B is equal to del cross A. Upon expanding determinant form, as we know that substitute x, y, z values by x by minus 1, y by 2 and z by 5, then we'll be getting the value as B. Then the flux through the surface defined by, so this is for A, and if you want to find B, see B can be expressed in terms of Weber per meter square or Tesla. Next is B. The flux through the surface defined by means flux is represented with psi, and in terms of magnetic flux density means integral S B dot ds. Okay, whatever the value which we have got from here, and that should be substituted over here, and ds. The formula for ds can be written as x and z are the two variables, means dx dz into ay need to be considered. So from this b, we are supposed to consider b in terms of y direction, and finally to simplify, then phi can be measured in terms of Webers. Okay, magnetic flux is measured in Webers. Next, if H is equal to YAX minus XAY ampere per meter on the Z equal to 0 plane, then determine the current density and verify Ampere's law by taking the circulation of H around the edge of a rectangle Z equal to 0. So, first we need to find current density. So, in order to find the relation between J and H, we use the notation as, the formula is del cross H bar is equal to J. Now, from this, J can be measured in ampere per meter square. Then after this, the circulation of H around the edge means we need to verify Ampere's law. The formula is given by here, closed line integral L H dot dl is equal to I enclosed, and that is nothing but integral S J dot ds. So closed line integral means we need to write this one as closed line integral H dot dl is equal to integral L, means x is equal to H dot dx ax plus integral y equal to H dot dy ay plus integral z is equal to H dot dz az, like this we are supposed to evaluate. And this is the case, whatever the value you are supposed to get, and this means I enclosed is equal to integral S J dot ds. And whatever the value which you are supposed to get here and here must be same. If these two are same, then it is to be verified Ampere's circuit law. Otherwise, it doesn't satisfy. Next, an electron with velocity u is given 3ax plus 12ay minus 4az into 10 power 5 meters per second. Experiences no net force at a particular point in a magnetic field B is given. Find E at that point. Means this is the case, we need to go for the Ampere's force law, that is Lorentz force equation, as F is equal to Q into E bar plus U bar cross B bar. See, from the given, no net force means F is equal to 0. Then Q value is given as under Q into E bar cross U bar cross B bar. Okay. So from this, Q equal to 0, hence E bar can be written as minus of U bar cross B bar can be obtained. Now from this, substitute U bar cross E bar by these two, means AX, AY, AZ, and in place of A, first we need to consider vector U as 3, 12 and minus 4, and in the B case 10, 20 and 30 to be considered, right? So which is equal to, now upon simplifying the total equation, E bar should be written as, along with this, minus of 10 power 5 into, here milli is given 10 power minus 3. Along with that, E to be expressed something into AX plus something into AY plus something into AZ need to be obtained. Why? Because this E bar is always a vector, right? So it should be expressed in terms of volts per meter. This is the way we are supposed to evaluate the electric field intensity from the Lorentz force equation. Next, a point charge of 10 coulombs moves with a uniform velocity of 2ax minus 4az meters per second in an EM field having E and B, and find Fe, Fm and the total force on the charge. Similarly, here also, first we need to find Fe, means electric force. So related to the electric fields means it is given by E into Q. So first Q value is given as 10 coulombs into E is given as, that is, AX minus 3AY plus 8AZ as the value. So 10AX minus 30AY plus 80AZ value is to be obtained for the electric force. This is for first one, A. Similarly for B, Fm means which is equal to Q into U bar cross B bar can be considered, which is equal to Q is again 10 coulombs into U bar cross B bar means U bar as 2AX minus 4AZ into cross product with B bar means, that is, 0.3AX plus 0.1 AY is to be obtained, right? So here if you want to get the value as Fm, then you're going to get sum. Then finally, to find the total force, F is equal to Fe plus Fm. By adding electric force and by adding magnetic force, then it becomes total force on the charge as F equal to Fe plus Fm. Or we can use the formula as for this is F equal to Q is a scalar, Q into U bar, Q into E bar plus U bar cross B bar. Right? Directly we can add Fe and Fm to get the value of F or total force, or else you can use the formula as Q into E bar plus U bar cross B bar is the other method. Next one is, in a certain material, Xm is equal to, where Xm stands for magnetic field susceptance, and it is given by 4.2, H is to be as 0.2x AY Ampere per meter. Now determine mu R, mu, and M, B, and J. Right? So to find this first one, Xm, we can use to find mu R, relative permittivity. That formula is given by mu R is equal to 1 plus Xm. So from this, 1 plus 4.2, which is equal to 5.2, need to be obtained as mu R. And similarly for second one, means mu need to be considered as mu naught into mu R. As we know that for a mu naught value, 4 pi into 10 power minus 7 into mu R as 5.2. So this is the way we can find mu and mu R. Then after that, B value. So to find this one, B, D. To find B equal to mu into H bar. So mu value which is to be obtained from over here, and H is to be substituted as 0.2x into AY, where B bar and H bar both are need to be expressed in terms of vectors, and B measured units is given by Weber per meter square. And in order to find J is equal to del cross H bar. So H is given. From this, we are going to measure the curl of the magnetic field intensity as H bar, hence it is J is equal to del cross H bar can be written. And we know that to find the C, then magnetic flux density B can be expressed as mu naught into H plus M. Now from this, B minus mu naught into H is equal to M, where M is the notation for magnetization, and it is to be obtained as B minus mu naught into H. Right? This is the way we can solve some of the problems which are exist in the analytical cases of magnetostatic fields. So in this particular lecture, we have learned some of the how to answer in the shorter answer questions and long answer questions, and in the critical or analytical type questions case, we will evaluate the problems and all in the magnetostatic fields we have learned in this particular lecture. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.